Good afternoon. Let's continue with the second lecture of the CFD course. This concerns the equations that govern the flow of fluids. The fluid dynamic equations are of two types. There are the balance equations, which describe the conservation of a quantity. For example, the principle of mass conservation leads to the continuity equation. Newton's second law leads to the momentum balance and eventually to the Navier-Stokes equations. The first law of thermodynamics leads to the thermal energy equation. If there are different species in the flow, if the fluid is made up of different species, then the principle of species conservation gives us the transport equation for each of the species. There may be other equations, such as the Maxwell or Boltzmann equations, which may also be relevant for a given application. Now, these equations by themselves are not complete. We require auxiliary or completion equations. These are the relations that are needed to complete data or the fluid properties to solve the equations. For example, there is the equation of state. The gas law or density as a function of temperature, for example, okay, that defines the relation for density. Then there are constitutive relations such as viscosity, diffusivity, turbulence models. So these come from either the molecular or the turbulence model considerations. There are fluid property relations such as specific heat and conductivity of host or host media or fluid media. And then there may be things such as porosity for the host media, or there may be other properties that are needed in specific situation. In addition, because these are evolution equations, they evolve with time, we require the initial condition, the initial state of a system that will then determine the final state. Then we need the boundary conditions, and these boundary conditions define what happens at the boundaries of the area of the finite area for which we are solving the equations. For any given problem, there may be specific other equations, such as if there is a heat generation in a room and we solve in the room, then we will require, for example, what is generating that heat? If there's an electric heater, what is the rate of input from that heater to the thermal energy? So all these other auxiliary equations, which would define a given problem, should be needed. Now let's look at how to derive a balance equation. It's really very simple. The balance of any property phi in an arbitrary control volume delta V, as shown here, with a bounded surface S and a normal N, right? So basic equation is that the rate of accumulation is equal to the net influx through the surface plus the net generation inside the volume. Okay, it's very simple. Don't be overwhelmed by complex equations. It's very important, I think, to think physics and not to think math. So what are these three components? The accumulation is basically that there is a certain amount of property phi. The total amount available is phi times the delta volume. Now, its evolution with time is given by d by dt. If volume is not varying with time, then this basically becomes d phi by dt times delta volume. If J is the outward flux at the surface, then the net outward flux, then the net influx of the phi is given by minus dot of J times N. That's the total flux leaving the area. So minus defines the input times the area. Finally, G is the rate of generation per unit volume. So that leads to per unit time per unit volume, and that leads to G delta V. Okay, so very simple. Now, so the balance equation is written in this form. Accumulation, net inflow, net generation. If we use Gauss theorem, we get d phi by dt is del dot G, J plus G. Very simple. just like your bank account. Savings grow, accumulation. Income in, expenses out, fluxes. Interest accumulates, source. Bank fees deplete the account, sink. Now let's look at the fluxes. Fluxes associated with transport processes can be of many types. Okay, but the most common ones are convection and diffusion. Those are the ones we'll discuss here. Radiation is another common flux, especially for heat transfer. But at this introductory level, we are not going to consider it. Now let's look at the net outward convective and diffusive fluxes at a boundary. The flux J at a boundary by convection is equal to the velocity that is carrying the fluid with it, property with it. So that's U times phi. Minus gamma, which is the diffusivity coefficient, times the gradient. Diffusivity is essentially a representation of the molecular motion, which is random and Brownian. On the average, X number of particles move from high concentration area to low concentration area, though they are fluctuating all around. The coefficient that determines that is called gamma, and it's the gradient that determines exactly what the total flux is. So the general transport equations, once we substitute for J, would become d phi by dt minus del dot convective term phi, diffusive term plus G. So if we combine all these terms and write in the index notation, we get the general transport equation that determines movement of any property. This is d phi by dt, storage change, accumulation, change in accumulation, advection or convection, diffusion, and source and sink. So this equation expresses the balance of any property that can move as long as we can assume a continua or a continuum approach. It does not apply to situations where there is no continuum, there are very few particles. Then we have to go to Boltzmann or some other equations. Otherwise, this equation applies to fluid, heat, mass, electrons, cars, humans, fishes, anything in large enough numbers that we can define as a continuum, stars in a nebula. So here are the common set of fluid dynamics equations. The mass density of the fluid, continuity equation, the three components of the Navier-Stokes equations, the enthalpy of the fluid, and a number of predefined mass species, such as these are very important for chemical reactions or for mass transport. In addition, many flows are turbulent, so we need some equations for turbulence or some model of turbulence. And typically we use either the K kinetic energy of turbulence with epsilon, which is the rate of dissipation, or the frequency, which is defines the size of the eddies. Okay. There may be other equations in addition, but these are the most common equations in regular engineering practice, unless you're in a very esoteric area. So let's look at the continuity equation. It basically can be derived from the general transport equation if we set the transported property to be mass density, and set alpha and beta equal to unity, that is the convection terms, and gamma to 0, because the total individual mass does not diffuse. The individual species can diffuse into each other, but the overall mass at any point does not diffuse. So that's that term, and then the equation simplifies to this simple equation: d phi by d rho by dt is del dot v of rho multiplied by rho plus the mass which is injected. Okay, very simple. Now Navier-Stokes equations are in the same manner, can be derived, and these basically say accumulation, convection, diffusion in, and then an important component that comes into play is the fluid pressure. This represents the normal component of the stress tensor, and that plays a very important role. And then, of course, there may be sources or sinks of momentum, such as fluids leaving, fluids entering, injections, and withdrawal, things of that nature. So this is the simplified version of the equations. we have ignored the second coefficient of viscosity, which is there in the Stokes formulation. We have done so because it's not important except for some situations of compressible flow. Navier-Stokes equations themselves are not complete. There are 4 equations, 3 for velocity components, 1 for continuity. Yet there are 6 unknowns: 3 components of velocity, fluid density, viscosity, and thermodynamic pressure. Now, density is either known or we have an equation of state for it, which comes from other consideration. So that's the fifth equation, sorry. Now, viscosity is known from the constitutive equations, okay? That's the 6th equation. But the problem is that you do not see any equation for pressure here, okay? The Navier-Stokes equations have a dp dx or dp dy, dp dz, but no pressure equation. That means there's no dp by dt term like d phi by dt term. So that's a problem, and we have to obtain the pressure from some considerations. For incompressible flow, density is a constant or is known as a function of, let's say, temperature. So what we can do, we know the viscosity, and from other reasons, from other considerations, so do we know now the density. So the 4th equation of continuity can be turned into an equation for pressure, right? So we have 4 unknowns, 3 velocities and pressure. We have 4 equations because the other 2 quantities are known. So for compressible flow, density is a function of pressure itself, right? So what we can do is we can put the density equation into the determine it from the continuity equation, and then we get pressure from the equation of state. Alternately, we can take the equation of state and put it into continuity equation and turn that into an equation of pressure. So these options will be discussed in more detail later. Now, the Navier-Stokes equations have been around since 1822, at least the Navier version. The Stokes part came in 1845, so they've been around for more than 100 years, right? Almost coming up to 200 soon. They are still one of the most challenging equations in physics. As of now, except for trivial cases, there is no known solution to the 3D form of the equations. Not only the solution, we do not have a proof of existence or smoothness of the solution in the 3 dimensions. The Clay Mathematics Institute has called this one of the 7 most open, intractable problem in mathematics, and has offered a prize of $1 million to anybody who either gets a solution or gives an example showing that there is no existence and no smoothness. Here's an opportunity for you. Now, since it was not possible to solve these equations analytically, and CFD was not yet on the horizon, over the years, many simplified forms of equations were derived for special applications. I would talk about 3 of them. There's the boundary layer equations of Prandtl, the shallow water equations of Stokes, or sometimes called the long wave equations, and then the porous media flow equation of Darcy. These are practically very important. These approximations are still used in many situations to verify the CFD solutions and to obtain quick and easy analytical solutions for back of the hand type of calculations. We will outline some of these simplified forms. Ludwig Prandtl in 1904 formulated the boundary layer equations. Before that, the fluid dynamics field had become somewhat stagnant because of the intractability of the Navier-Stokes equations. So this insight by Ludwig Prandtl resulted in new vigor and groundbreaking progress in many fields of engineering, especially in aerospace and also in the naval field. In many practical problems, and this was Prandtl's insight, the change of flow in one direction is much more rapid than that in the other directions. For example, take a flat plate. A boundary layer develops and its thickness delta, normal to the plate, is much smaller than the scale of flow L in the other two directions. That means the plate is much larger than the thickness of the boundary layer. Delta is much, much smaller than L. If we put this order of magnitude analysis in the equations, we'll see that the diffusion, axial diffusion terms in the U velocity equation are small compared to the other terms. The second thing that happens is that the equation for velocity component normal to the wall, the V velocity, drops out because all the terms in this equation are of the order of delta L or smaller. So the 2D Navier-Stokes equation then reduced to this simple form, the convective component plus the diffusive or the stress only in the normal to the plate, the Y component, and pressure gradient along the plate. The V velocity equation is absent and the continuity equation is given here. So there are three variables here, U, V, and P, but it so happens that under these assumptions, pressure is a known quantity that is computed from the free stream conditions. In other words, if you do the basic analysis, you will see that the pressure gradient is determined by the outside flow, not by the boundary itself. It's imposed on the boundary. So if we know something about the outside flow at the free stream end, that will give us a condition for the pressure. Okay. So with this, the equation is complete, the pressure is known, and the equations can be solved for U and V. This resulted in a great progress, and also the same equations are applicable with some variations for jets in an infinite surrounding or along the walls, and also for wakes behind solid bodies such as cylinders. So much of the progress made in these. Shallow water equations is another useful assumption. This is used for large water bodies such as oceans and lakes, where the depth of the water is small compared to other representative lengths, such as the horizontal extent of the water or the curvature of the surface, or the long waves are much longer than the short waves, which are with the depth. So if we put this order of analysis in the Navier-Stokes equations and integrate with depth, it yields the 2D shallow water equations, which are proved very useful for coastal bodies and for other large lakes and large water bodies. So let's look at this equation. What happens to the equation is that Navier-Stokes equation, the convective terms stay, the pressure term stays, but now this is the pressure which is known measured atmospheric pressure. Okay, we're looking at atmospheric pressure above the water body, which determines the flow of the water in the ocean. There is the curvature of the earth. Omega is the Coriolis parameter. So that gives us the Coriolis force that is imposed on the water body. Since we integrate with depth, the diffusion terms drop out, and we only have the friction at the top and the bottom. The top is due to the wind, friction due to the wind that moves the water. And then at the bottom, friction that slows down the water through friction. So that's the two coefficients. It's the wind is proportional to the speed of the square of the speed of the wind and the angle cos theta with the grid. And the friction at the bottom is given by this formula, which is the net speed multiplied by the U component velocity and skin friction coefficient. Then there could be sources. Often there is injection or withdrawal of water from the water body. So those are the sources that define mobility. Similarly, in the Y direction, the same thing happens, except that you have the Coriolis force, you have the wind force, except that now it's a sine theta, and you have the friction as before. Now the continuity equation takes a very interesting and simple form. Let's assume that there is a calm sea surface called the datum level, or let's say the sea level. Now the total water depth at any point can be composed into a time constant factor, which is the depth below the datum. Let's say there is a sea level. The depth below that level is constant because ocean bottom, we hope, is not moving. And the amount above is the departure from the total depth. So that is, we denote the departure by eta, total depth by h, and the depth below datum by h. So if you put this in the equation, we get velocity, density is constant for the water, we assume so. And we get d eta by dt, that is the change of the water surface level of water, is equal to the flux that comes in throughout the depth, h times the convection, throughout the depth, the total water that moves through convection. And this must equal the net injection or generation or withdrawal or whatever you have it, which is where MV is the vertically averaged mass injection per unit time per unit volume and multiplied by H. The third approximation is at the other end of the equations, where we assume, let's take a porous media such as earth, ground, okay? Now here, the water moves very slow. It's essentially a creeping flow. The typical Reynolds number is below 10 based upon the grain size. So the Navier-Stokes equations, then basically the momentum equation just degrades to this very simple form. Velocity is equal to a conductivity, a factor, which is called hydraulic conductivity, times the pressure gradient, and then the force due to gravity, that is, or due to buoyancy. Okay, so that is basically the equation. Pressure here, often in groundwater, is defined in length units. Okay, like you talk of so many meters of water, or you talk of millimeters of mercury, right? So pressure here is normalized with a thermodynamic pressure minus a reference basis. Quite often we use atmosphere as the reference. So it's the pressure above atmosphere or below, divided by the mass density, which is the reference density, and the gravitational component. This gives you the units of length. Hydraulic conductivity is defined as the permeability, which is a property of the host media. It essentially is equivalent to the total surface area of the grains which are constitute a certain volume. It basically represents that. Okay, that's what causes friction, is when water touches all these and there's friction there. So this is normalized with the velocity. Okay, it's called conductivity. When the velocity is high, the conductivity is low. When the viscosity is high, conductivity is low. When viscosity is low, conductivity is high. Okay, this is the friction basically. The buoyancy force is just basically the ratio of the actual density to the reference density, and the gravitational component versus in that direction versus G. Generally, there is just, it's present only in the vertical direction. The continuity equation degrades to this simple form. Okay, if theta is the porous effective porosity of the media, then the fluid can only be present in the porosity. It cannot be present in the solid, right? So that is that the total amount of fluid at a place is the density multiplied by the porosity. And then this is the convective term like before, and this is the mass injection. Okay, so this is the Darcy equations. This will come very handy for groundwater flow applications. Now let's move on after this to other equations. Most important of these is the thermal energy. So many problems of practical interest involve heat transfer. Here, a number of different variables are used to denote the balance of thermal energy, and this depends on the applications which are of interest to us. For example, temperature is one. Another common variable that is used instead of temperature is total energy, CV times T, where CV is the specific heat of the constant, that the internal energy. Then there is the enthalpy, which is the specific heat at constant temperatures times D. Actually, this should be integral of Cp dt. Then there is the stagnation enthalpy, which is basically puts the kinetic energy of the fluid and the turbulence together with the enthalpy to form what is called stagnation enthalpy. This is very important variable when flow speed is very high, such as near sonic or supersonic. And then these components, the kinetic energies become very significant, and they may even exceed the thermal energy. So which option is most suitable depends on the application. If you're talking of reactive flow, combustion, things of that nature, then my preference is for enthalpy. The reason for that is that once you put enthalpy, the heat of formation is included in the enthalpy of the fluid component. So therefore, you don't have to explicitly deal with things like latent heat. Okay, so this makes it very advantageous. Also, you don't have to deal with specific heat. It's part of the enthalpy, and specific heat is buried in there. So when you come, as I said, when you come to high-speed flow, the kinetic energy can be significant. And so therefore, it's better to look at the conservation of total energy, where one energy form, the kinetic energy can move to thermal and thermal to kinetic through dissipation terms. So the enthalpy equation in terms of stagnation enthalpy is this one. Okay, this should be sub S. So basically, it's the convective term as before. This is the diffusive term, and this is the source. So here, K is the thermal conductivity, or it could be for turbulence, it could be effective thermal conductivity. Now here, the stagnation enthalpy is defined as the enthalpy of each component. Okay, for reactive flows, there'll be multiple components, multiple species reacting with each other. So we have mass concentration, mass fraction of each species multiplied by its enthalpy, plus, of course, the kinetic energy component. Now, enthalpy of each component is given by the heat of formation, so that eliminates the latent heat or the heat of formation, plus the integral of Cp with temperature. So this basically makes it a very simple equation. The other term that is very important, especially for combustion or many other applications, those in pollution, for example, there are multiple species that are carried in the fluid. So conservation of each of these species is given by this equation. Basically, again, the convective terms, and then the diffusive term, and then the sources. This is the decay, such as radioactive decay, which is proportional to C, the concentration itself. Now, it should be noted that this expresses the conservation of species in a single phase and of one species, right? C is the total amount of that species in that fluid, okay? If there are multiple species, you may have to solve for as many terms as many equations you have to derive as this one, and one equation, of course, with the total amount, so it will be n-1 if there are n species. Then you can express the conservation laws for these species for that space of fluid. Now, when we're dealing with transported media such as the Earth, a given species may be present, a nuclide, radionuclide, for example, may be present in the solid, in the ground part, in the grains. It may be present in the liquid, or they may be gaseous, air phase that is in the ground. So in such cases, the conservation equation must be modified to take account the transport in multiple phases. In other words, now there'll be each species moving in each phase, okay? So this becomes a fairly complex problem. And so you have to take account of this, and then one species may be turning into another. So these source and sink terms become very complex, and they represent the transfer of species from one species to another, or degrading or agglomeration. So these are the species conservation equation. Now we come to the turbulent part. Most practical flows are turbulent. Okay, we'll be dealing with this in a later talk. But for the present purposes, let's assume we are going to use a two equation model, and I'm going to take it to be the K epsilon, which is kind of a standard model, though increasingly there are blended models and there are models that use K omega or K omega E kind of blend. So K is the kinetic energy of turbulence. This is the energy that is above the mean velocity, above the mean flow velocity, right? That's the kinetic energy of that component. So this says that the transport of that through convection and accumulation is equal to a diffusion that occurs. And this diffusion, of course, is due to the eddies mixing with each other and the other random movements. And there is a production term that comes, okay, which we will define. You can go to standard book to find out. And then there is, of course, the epsilon, which is the dissipation. So the kinetic energy is transported, diffused, generated, and dissipated. Now we can write an equation for dissipation term itself, and that equation looks like that. It has two constants, epsilon 1 and epsilon 2, and these are the common way of writing those terms. If you write the K omega model or the frequency model, then this equation would be somewhat different and new terms would come in. So this is an area of very active research, and there are many other turbulence models such as LES and such as DNS and such as Reynolds stresses models and all those. I'm not going to talk of them now, but we'll cover some of that in a detailed lecture. The two other equations I'm quickly going to bring to your notice before we wind up are the following. Maxwell equations become very important when electrical or magnetic components forces become significant. This can happen, for example, plasmas are always like that. In nuclear field, there are electrical or magnetic forces, okay? So these are governed by the Maxwell equations, okay? These equations are basically fairly simple, okay? But here is a list of equations for your completeness. Here E is the electrical field, B is the corresponding magnetic field, rho in this case is not the fluid density, it's the charge density, okay? And then J is the current density that occurs here, and epsilon 0 is the permittivity of the free space, and mu 0 is the permeability of free space. So these basically define, if you want more details, you can get them from any standard textbook. The last equation I'm going to talk about is Boltzmann equation. Actually, this is the most general equation for fluid flow, okay? This can be made to apply to discrete forms of the equation when there is not enough particle present to make a continuum, or this can also be applied when the Knudsen number becomes large and you have very few particles at a point, okay? So this is the basic equation, and what this says is that let's define a function f, which is the particle distribution function. This is how the particle is distributed. And this is their motion is represented by u delta f, and omega is the collision operator. Now, how does collision happen? You can think of collision, as I said, at molecular level. Diffusion is a collision phenomenon, okay? There are a number of particles in random motion. When there are enough of them, then we can say that they're proportional to a constant or coefficient times the gradient of the concentration, right? But when there are not enough of them, then the collision operator have to be obtained from some manner. Quite often one assumes, for example, that particles are spherical or that they're hard and they just bounce off each other when they interact, okay? So this is the proof of the Boltzmann equation, or rather the way we get the Boltzmann equation is the collision factor is where the kernel of the problem is in defining using the Boltzmann equation. There's a lattice Boltzmann method that we'll talk about briefly in a later lecture, which will take you through some simple formulations of this equation. Okay, so this is basically completes our discussion of the governing equations, and I like to have this table of coefficients, which we used to go back to my Imperial College days. This comes very handy when we're writing a program to solve a general equation. So you can see here a simple table under some certain assumptions, and you can do it for your assumption, where if the variable is replaced by these, and these are the alpha, beta, gamma of the equation, and then these are the sources. Okay. So, fluids surround us and fluids are in us. I'm very fond of reading mystery novels. Coding a CFD program to me was not that different from solving a mystery. Where are there coding errors? Does the result represent a real solution? When you come back with a dump, where does it occur? When the solution shows something which is unrealistic or downright stupid, what went wrong? So you have to get a clue, look for it, and find the cause. Who murdered your solution? So satisfaction you have once you've solved all the mysteries and worked through the vagaries of the operating system. Don't forget, the operating people like to change the system just as you get used to it. And then the languages change. I started learning with Fortran, and now I don't think Fortran is even taught in any place. So it has been a big mystery, and nonetheless, it's a great thing when the result is in front of you. CFD is fun. I want to remind you again, thank you very much for your time.